about plant sex. And actually, we're going to be talking about alternation of generations.
What have you been doing? Yeah, I know.
A game
right.
that
Oh,
plants
stop
are playing
dying.
that I like
Stop
to call
that.
hide the gameta fight.
Maybe your accent.
So, if you don't think about plants very
Sorry,
often,
sir. This is
they really do have kind of a tough go.
You're getting away.
Plants need to be able to find each other to have sex.
Sorry,
Plants also need their offspring to disperse far away from
Please
the
don't
parent.
alone
So
right
they don't compete
now.
with each other. You don't want to compete with your offspring for resources.
Stop it right
the problem
there.
is, of course,
Here.
plants
no
don't
food
move.
allowed.
And so
No
the
drink
question
allowed.
is, how are you going to get your gametes, your sex cells, how are you going to get those together? How are you going to find members of your own species? How are you going to find another individual to have sex with?
No. You're
And what happens when you finally do have offspring? How do you get them far away from you? These are difficult questions. This story is really going to be about sex and life cycles. And like everything, I think it's good to start with something you're familiar with and then build information that may not be so familiar so that your brain comes. So what if we had this scenario? We have an egg, and we said that plants have 46 chromosomes, right? And then what if that egg gets fertilized by a sperm, and that sperm also has 46 chromosomes? Okay, what you have there is a complete disaster, because then every time you have fertilization, you would double the number of chromosomes that an organism would have. You just can't have that. So instead, what we have is egg cells half that number, 23 chromosomes, and a sperm that has half that number, only 23 chromosomes. And then when you have fertilization, it's so much better. Now you have the correct number of chromosomes again. So the vocabulary that we use to talk about chromosome sets is called ploidy. And you're going to see these terms a lot. Haploid, the number of sets in sex cells. So eggs or sperm, they have only one set of chromosomes. We use the letter N for haploid. And then diploid is 2 sets. And that we're going to find in all somatic cells, other cells in the body. The word soma, by the way, just means body. There are other terms, by the way, especially in plants. You'll see tetraploidy, polyploidy, but for now we're just going to stick with haploid and diploid. That's going to get us through the story that we need. So the human life cycle, with which you are familiar, looks something like this, where we start out with adults, which are diploid. The cells of your body have 46 chromosomes. In cells of the ovary or the testes, you have a very special type of cell division called meiosis. Right? So meiosis only occurs in gamete-producing cells. And meiosis is what takes the cell from diploid to haploid. It also creates variety because there's a shuffling of genes, right? Because if you've got to reduce the number of chromosomes by half, then obviously your egg or sperm only gets half of what you've got, right? So now we go from a diploid state to a haploid state. So now the egg and the sperm are each haploid cells, and only at fertilization is the diploid state restored, right? So egg plus sperm, 23 plus 23. Now we've got a diploid, we call it a zygote, a fertilized egg. And for humans, N is 23, right? So we have 46. Just so you know, of course, different species have different numbers of chromosomes, so the N value will change. But the haploid, diploid, right, that stays the same. So now we've got a fertilized egg. It undergoes mitosis. That's replicative division, kind of like a cell, going through a Xerox machine, basically. And that happens over and over again, and you end up with a diploid adult. Okay, so if we're to simplify this, so we're going to be able to compare animals with which you're familiar to plants, which may be a little more unfamiliar. We have this, where you have a diploid adult, right? Everything above the line is diploid 2N. We have meiosis, which is our magic cell division, and the product of meiosis for animals, the products are gametes, eggs, and sperm. This is a big difference that we're going to see from plants, so keep that little fact in mind. For animals, the egg and the sperm come together, fertilization, right? We just saw this. Now you restore the diploid condition. You got some mitosis, and now you're back to an adult. Okay, so hang on to your ad
You're
notes,
right
because
now.
this is what
You
the
thought
plants
you
do.
like
Plants
this
are
tutorial.
kind of foreign to
You're
us
right
because
now.
they have a
I'm
whole
starting
extra
this,
step.
but I didn't
We're going to start with the
actually see
diploid
it.
adult, which
I
would be
told him
equivalent to an animal.
place
We're
here.
going to call
Yeah,
it
I
a
know. Isn't
sporophyte.
it great?
Okay, and that is
But
diploid. This 2N should now be familiar.
I see it.
That sporophyte is going to undergo that special type of cell division called meiosis. But what you make in a plant is not eggs and sperm. The product of meiosis in plants is a spore. The product of plant meiosis, spores. These spores are haploid, and they undergo mitosis, and they grow up into a haploid body that we call a gametophyte. Oh my goodness. So this would be, an equivalent in humans would be, if you could imagine your eggs or sperm leaving your body, and without fertilization, they grow up into you, but it would be a haploid you. Okay, that is pretty weird, and animals don't do that, but plants do, and that's why plants make a lot of people a little bit crazy as we try to understand them. This gametophyte will undergo mitosis and produce eggs and sperm, which are called gametes, just like animals, which will fertilize, just like animals, and restore the diploid condition, just like animals. That diploid zygote, the fertilized egg, undergoes mitosis and grows into a sporophyte. So this is what you've got to remember with plants. Sporophytes produce spores. Gametophytes produce gametes. So if you can remember this, say it to yourself over and over again, and keep in mind that the product of meiosis in plants and animals, the product is different. In animals, meiosis produces gametes, eggs and sperm. But in plants, the product of meiosis, spores. If you can keep those things in mind as we go through the various plant groups, you're going to be okay. We're obviously not going to be able to go through 480 million years of plant evolution on a YouTube video. So, though you know I would love to try, we're going to talk about a few main groups of plants that will illustrate the difference in the alternation of generations story, which is really what this video, of course, is about. We're going to start with the mosses. Mosses are in a group called bryophytes, and with mosses we have other less familiar plants like liverworts and hornworts. They all have pretty sexy names. When you look at a moss, mosses of course grow in very, very moist places in the forest and things like that. They need a lot of water because mosses are non-vascular. They don't have any vascular fluid-carrying tissues. That also keeps the size of mosses very small. When you look at a moss, what you're looking at is actually the gametophyte. We see the sporophyte in nature. Mostly you see the gametophyte. That's all that fuzzy green stuff. But this is what the sporophyte looks like. And you'll only see it during certain times of the year. So again, the dominant phase in a moss is the gametophyte. Now let's compare the story of mosses to a more highly evolved plant, the fern. And when you look at a fern, this is the sporophyte stage of the fern. By the way, ferns, beautiful plants, these are vascular plants, so they can get much, much larger than mosses. There's about 12,000 different varieties in this group, and they really started to dominate during the Carboniferous period. That's about 380 million years. It's microscopic, so unless you go out in the forest with a microscope, you're never going to see it. This is called a fern thallus. It's kind of a heart-shaped thing. Isn't that cute? It's got archegonia, which are female parts, and antheridia, which are the male parts. They only find each other in water, which is why ferns are also very rare plants. So here is a pine tree, and hopefully everybody's familiar with these. When you look at cone-bearing plants or conifers, these are all sporophytes. Okay, the gametophyte has gotten smaller still. The gametes are actually hidden inside the cones. Oh my goodness, I know these life cycles can get a little bit overwhelming with all the terminology, but they're actually just variations on the same story. So we're going to start with, again, the phase that you see in nature. This is the mature sporophyte, right? This is the tree. And the tree, in the cones, we have, of course, meiosis. And the products of meiosis, of course, are spores, and these are haploid.
There's
This
a
actually is
tail
going to
like
take place
this.
within the cone.
Or a
And at
dog.
fertilization, of course, there are male and female cones, by the way.
No,
Female
it's
cones are
not.
more conspicuous.
No, it's
Male
not.
cones, which
I
produce
have to
pollen,
shoot.
they
my
basically,
God,
after they
you're
release
from-
their pollen, they just wither away and you don't
I
really
know.
see them.
Isn't it right?
Of course,
Come after
conifers
me,
rely
right?
on wind for dispersal, right? So it's just a mass of pollen in the air from these guys when they are breeding. During fertilization, the diploid state is restored, of course. Now we have our zygote, and it develops within a seed. And that seed will sprout and grow an entirely new sporophyte.
Come after me.
The most advanced of all plants, and certainly the most beautiful by most people's estimation, are the angiosperms. And these are the flowering plants. This is a cherry blossom tree, and in nature, what dominates in angiosperms is the sporophyte. And the gametes are actually hidden inside the flowers. So the flower is the sex organ of the flowering plant. And I just gotta say right now, it's really no coincidence that flowers are a symbol of love and romance. If you give a woman a corsage, that's not a subtle message, right? You're basically saying, wear this sex organ and think of me. Okay, so again, the diploid state is what we're going to start with. The plant itself is sporophyte, right? So here's a really nice flowering plant. And within the flower, you have meiosis going on to form the egg, and in this case, the pollen grains. And the plant has to pay for that special touch in a lot of cases. Now, some angiosperms are also wind pollinated, but a great majority of them make big, bright, showy flowers to attract pollinators. The problem is, of course, that that's expensive. Flowers have to pay for service in the cold, hard currency of nectar, right? And of course, if you're pollinated by birds, it's going to cost you even more. But for the plants, it appears to be worth it, as the pollen is delivered from flowers far away. The pollen grain will stick onto the stigma. It actually fits very precisely. This is to prevent pollination across different species. So it's kind of like a lock and a key right here. And then the pollen grain will grow a tube and grow all the way down to the egg. You have fertilization, diploid condition is restored, and now you have the development of the embryo within a seed. And for even better dispersal, the ripened ovary becomes a fruit, and the plant will pay even more to get its offspring far, far away from the parent plant, and you make it nice and juicy and tasty so that seed dispersal can occur, and birds and mammals will eat the fruit, digest the seeds, activate the seeds, and then deposit them in a nice pile of fertilizer far, far away from the parent plant. Oh my goodness, even dispersal is expensive for plants. So the summary of the story is that as we look through evolutionary development of plants, as plants become more and more complex, that increasing complexity means you have to have more genes, and the more genes you have, the more likely it is that you're going to be safer as a diploid sporophyte than as a gametophyte. In other words, the gametophyte phase, because you only have one copy. If something bad happens and you have a lethal error in a gametophyte stage, you're out, right? But if you're a diploid sporophyte, you have a backup copy. So you want to spend more and more time as a diploid sporophyte, the more genes you have. And this certainly holds true for animals as well, right? So we spend more of our life cycle, much more, as a diploid organism, and a very, very small amount of time as haploids. So that is the story of the hide the gametophyte game that